My name is Steve Boggs. I'm the chair of the physics department here at Berkeley, and I'm really excited that Berkeley can help host the Berkeley Prize Symposium this year. And of course, I'm very excited for the physicists who won today. So Berkeley had, in addition to, of course, our involvement in Daya Bay with Cambu, Luke, who we're very proud of. Congratulations, Cambu. Berkeley has had substantial involvement in both SNO, which you'll hear about a little bit more today, and in ChemLands. So that was Stuart Friedman, who passed away, unfortunately, a couple years ago, but very heavily on our minds today in today's awards presentations. So the discussion this afternoon is on the future of particle experimental physics. And oddly, we had no idea about the selections this year when we chose that subject. So, so I think we did a good job picking that topic. And so we're going to hear about the full spectrum of particle physics, not just the neutrinos, but they are certainly a critical part of that. So the way that we're going to structure this today, we're going to have 15-minute presentations by 5 different speakers. We'll have time for very brief questions for each speaker afterwards, and then if there's time at the end, we'll bring them up for a panel. So, but we'll have to play that by ear and see how time goes when we get to the end. So our first speaker today is Nima Arkani-Hamed, who is coming from the Institute of Advanced Physics. He's a particle theorist, and he won the Breakthrough Prize in 2012. So I think a good person to start off our presentation. So Nima?
Thanks a lot. Well, it's always fantastic to be back here at Berkeley. And our topic today is the future of particle physics. So what I want to, I'll be talking about motivations for great big circular colliders, maybe 100-kilometer scale colliders that can operate as Higgs factories in a first run as E plus E minus machines and 100 TeV proton-proton colliders after that. But since the topic is the future of particle physics, I want to spend, because it's very important for the subject, I want to spend a few minutes talking about why there is a future for particle physics, okay? Because it's not a completely obvious question. People say, look, before the LHC, we had a very good expectation that we would see something like the Higgs, a new particle, or Higgs or something like it. And now when we go beyond, we don't know where the next milepost is. We don't know for sure whether the next colliders are going to discover new particles. So how can we possibly justify continuing? It's a very important question, and we have to confront it head on if we're going to talk about the subject. And part of the misconception is what particle physics is actually about. One of the sort of popular pictures for what it is that it's a study of the basic building blocks of matter. That's one aspect of it, but it's not the most interesting aspect of it. The most interesting aspect of it, it's not merely the study of the building blocks of matter. We study these elementary particles ultimately because we care about what they tell us about the fundamental laws of nature. And what we discovered in the early part of the 20th century is that the story of the fundamental laws is most effectively told by studying the interactions of the elementary particles at the highest possible energies. And they're governed by the still mysterious union of the ideas of space-time and quantum mechanics, the two big revolutions of the early part of the 20th century that we understand well enough to construct this fantastic edifice of the standard model of particle physics, but which leaves us with many really fundamental paradoxes left as we go to the 21st century. So saying this all again, is it true that new physics means new particles? If our definition of new physics is that we have to guarantee before going to the next frontier that we're going to discover new particles, we should quit right now, because we can't guarantee that. That's the honest statement. But new physics does not mean new particles. We care about new particles because they're a stand-in for something more important. We care about new phenomenon and new principles. That's what we really care about. And from that point of view, we're actually in an incredibly interesting, almost unprecedented situation in the history of our development of our subject. That can be sort of summarized by this slogan. A big summary of what we learned in the early part of in the 20th century is whatever the underlying laws of physics are, compatibility with the pictures of space-time and quantum mechanics guarantees that at long enough distances, we'll have elementary particles. The physics will be described by elementary particles interacting in the simplest possible way with 3 particles coming together at points in space-time. And that the elementary particles have to be picked from a menu of spins of particles that have spins 0, 1/2, 1, 3/2, and 2. That's something that can be determined almost from pure thought once you know these basic principles of relativity and quantum mechanics. That's something we knew on theoretical grounds, and the story of the Higgs is essentially part of the completion of this story. We discovered the Higgs on July 4th, 2012. That turned that red 0 into a black 0. We finally saw an elementary particle of spin 0. It plays a crucial role in allowing us to connect the physics of massive particles at very long distances to massless particles at very short distances where their interactions are so incredibly constrained by these general principles. And that's what's so important about the Higgs. It's the first really new elementary particle we've seen. We've never seen an elementary particle of spin 0 before. And its existence is tied up with all sorts of other mysteries. On the one hand, if we posit that it exists, the kinematics of how to describe it are well controlled by our understanding of relativity and quantum mechanics. But on the other hand, from many points of view, it's very mysterious that it should exist at all. Here is a famous one. If we look at something as simple as the energy in the vacuum of the universe, we add up the ½ h bar omega for all the harmonic oscillators for the particle of Boggs modes for every particle in the universe. It has contributions which are enormous, sensitive to very high energy scales. The leading contribution is the energy density of the vacuum. That should curl up the universe by all rights to a size of 10 to the minus 33 centimeters, and it hasn't. That's the cosmological constant problem. But there's a sub-leading piece to that, which has to do with the dependence of the mass of the elementary particles on the Higgs. That should give the Higgs an enormous mass, 32 orders of magnitude bigger, or 16 orders of magnitude bigger as a mass than we've observed. And these are both associated. This is the cosmological constant problem. This is the hierarchy problem. And it affects the Higgs in that sub-leading term precisely because the Higgs is a particle of spin 0 that has the opportunity to have a mode that fills the entire universe. Here's another aspect of it, which more clearly illustrates why spin 0 is a problem. We understand why a particle like the photon is massless because of a discontinuous difference between the number of degrees of freedom of massless and massive particles with spin. Okay, a massless particle with spin has 2 degrees of freedom, a massive has 3, and so there's no way that interactions with virtual particles in the vacuum can discontinuously convert a massless spin 1 particle to a massive one. Not true for spin 0 particles that have exactly the same number of degrees of freedom for massive and massless. We have no good understanding why the interaction with the virtual particles in the vacuum don't give the Higgs an enormous mass. So it's the first really new elementary particle we've seen. And in this sense, it's really new physics. It's a new phenomenon. We've never seen anything like it before, and you don't discover something new that you've never seen before, especially one that's tied up with the drama about quantum fluctuations in the vacuum and just walk away from it. Okay? So it's really new physics. We've never seen anything like it. Many people think it's a harbinger of some profound new principles at work in the quantum vacuum, and so experimentally, we just have to look at it closely. So there's very obvious questions associated with it. We've never seen a point-like scalar. The picture of the Higgs that we get from the LHCs, it looks roughly elementary. In other words, its size is a little bit smaller than its natural Compton wavelength. Okay? But not so much smaller. And there's a very natural question. How point-like is it? That's something for experiment to answer. That's a question that today we know the LHC will not answer. Okay? It won't do so much better than it's done already. Just to drive this point home, what we know with LHC resolution today, and what we're likely to know through the final run of the LHC, is that the Higgs could be about as elementary as a pion. A pion was a spin 0 particle, and it's also relatively light compared to its Compton wavelength. Okay? So it has a size which is smaller, about 5 times smaller than its actual Compton wavelength. Its size is set by, for example, the mass of the rho meson. Well, that's about the picture of the LHC that we're going to get. That's about the picture of the Higgs that we're going to get from the LHC. So it's possible that even though it looks like it's an elementary spin 0 particle, and there aren't a lot of other friends around, that it's about as elementary as the pion. It would be great to know if the Higgs is composite. It would be great to know if the Higgs is something like a pion. But its implications, whether it is or isn't, are gigantic, right? I mean, if it is, it's another layer of the onion. It's very important. We'll have to understand it. If it isn't, it's much more theoretically dramatic, right? Then we really are in completely uncharted territory of a sort that we haven't seen before. We have to decide this question, not theoretically, but experimentally. Okay, there's lots of theories that make the Higgs something like a pion, but we'd like to know experimentally whether that's possible. Okay? So in order to do that, we just have to study it. Okay, so we have to, instead of having the fuzzy picture, this is the picture of the Higgs that we'll get from a Higgs factory. Okay? By looking at how the Higgs interacts with other particles, almost literally like looking at it, instead of with photons bouncing off of it, you see how a Higgs decays to couples to 2Z particles. Okay? That's going to give us a picture that looks much, much more like this. Okay? It'll increase the resolution compared to what we get from the LHC by a factor of 10 or 20 or 30. And that's what's needed. For example, if we do this at a Higgs factory, we'll know for sure whether the Higgs is like a pion or not. Okay? And if it is like a pion, there'll be deviations in the strength of its interactions compared to that of a point-like picture. And if not, not. But we'll know definitively the answer to that very important question. Here's a quick plot just to give you an idea of the leap in precision that you can get at a Higgs factory versus what you can expect from the LHC, and I won't have time to go through it in detail, but across the board it's a factor of 10 or 20, and in some of the most important coupling constants, namely the coupling of the Higgs to 2Z particles, it's almost a factor of 30 better than you can do with the LHC. It's fortuitous that the one that you do the best with at this machine is the one that has the deepest theoretical significance and is the cleanest measure of whether the Higgs is composite or not. All right, now there's one more important question associated with whether the Higgs is point-like or not, which is the following. Does the Higgs look point-like to itself? Okay? It might look point-like to other things, and yet not look point-like to itself. In fact, the self-interaction of an elementary particle is perhaps the most basic process we can talk about in quantum field theory, and yet no elementary particle other than the Higgs can experience it. Okay? We think that gluons can interact with each other, W's interact with each other, but they always change a quantum number. They change a color or flavor or some quantum number. The only particle that even has a chance to interact with itself is an elementary spin zero particle. So you have to go look, does it interact with itself? It's a brand new kind of interaction we've never seen in nature before, the most basic, simple possible one. And the LHC is not going to be able to tell us even whether this interaction exists, never mind measure it. Okay? That's what you need. For that, you need to make hundreds of millions, billions of Higgs particles, enough so that this process happens at a sufficiently high rate that you can actually see it and measure it. And that's ultimately, that's the actual rock-solid physics case. That's one of many things that going to a 100 TeV proton-proton collider will do, produce enough Higgs particles in order to be able to actually see that process and perhaps measure it to the 5% level, 5 to 10% people. People are fighting right now about whether it's 5% or 15%. My bet is that eventually it'll settle down closer to 5% or even better as people start being more imaginative with how they go about doing this. Okay, so it goes from not knowing whether this interaction exists at all to being able to actually see it. All right, so those are the most basic questions about the Higgs, this new object. We have a very fuzzy picture of it from the LHC. We're bound to continue to have a relatively fuzzy picture of it from the LHC, and that's what these facilities are going to allow us to do. Of course, a 100 TeV collider does something else. It blasts into the energy frontier, and that's something that we've been doing for 100 years or 50 years, depending on how you count. And so there's absolutely no reason to stop doing it now. If 100 TeV seems crazy, I'll just remind you that it's only 2 times more powerful than the superconducting supercollider, which is something we were going to do 30 years ago. Okay? So it's pathetic if the human race cannot, 50 years after we first started doing about it, go a factor of 2 compared to what we could do back then. This is not crazy technology. It's not, it's not la-di-da thinking. This is something that we can do, and there's absolutely no reason we shouldn't keep doing it. But by going to these higher energies, we will have power to produce new particles at 10 times, roughly 10 times the reach of the LHC in mass, more like 5. Okay? 5 to 10 times the reach of the LHC in mass. And importantly, the probe of the quantum fluctuations in the vacuum scales like the square of the energy of the machine. So it gives us a probe of those quantum fluctuations with a power 100 times larger than the LHC. Okay, so there are various ways, if you want to speak more professionally, about very concrete physics questions that these machines are going to tell us something quite robust about. If you ask the question, for a long time we wondered what breaks electroweak symmetry, and now we know the answer. It's the Higgs particle, the Higgs field getting an expectation value breaks electroweak symmetry. The next obvious question from there is how is electroweak symmetry restored as you go to much higher energies, or as you go to much higher temperatures in the early universe? Okay, so that question about the nature of the phase transition to restore electroweak symmetry is something that we'd like to explore experimentally. And anything which affects the nature of this phase transition is bound to give you percent level deviations in the couplings of the Higgs, as well as new particles that are accessible to the 100 TeV collider. There are questions involving why the Higgs particle was like to begin with, the infamous or famous, depending on how you think about it, question of naturalness. This is something that was a huge motivation for the construction of the LHC. We haven't seen any of the particles that were suggested by these arguments yet. Okay? It's not obvious that that means they're not there. There's something a little bit wrong with the way we're thinking about it, or there's something a lot wrong with the way we're thinking about it. We just don't know. The only way we can decide is to go and look. I want to point out something that David Gross keeps emphasizing whenever we talk about these things, that never in history has it been true that to understand physics at an energy scale E, it suffices to go to the energy scale E. You go to 10E. You go to 10E so that things aren't confused and you're not in transition regions and you really get a picture of what's going on. That's really what happened with QCD. The characteristic scale of QCD is 300 MeV. And if we're stuck at 300 MeV doing experiments there's no way in hell we would figure out that there's quarks and gluons underneath the whole thing. That needed just to go to 2 or 3 GeV in order to see that picture emerge. Okay? And finally, the idea that dark matter might be weakly interacting particles. And the very simplest picture for what dark matter could be, their mass is something that's not accessible to the LHC. It's just tough. The simplest pictures of dark matter have these particles weigh 1 TeV or 3 TeV. They cannot be produced at the LHC, but they will be produced in a 100 TeV proton-proton collider. All right, so there are some technical things that I don't have time to go into, but let me just finish by making the most obvious remark that here we're talking about the long-term 2 or 3 decade future of particle physics, but right now we're probably entering or in the most exciting phase of the running of the LHC. And almost all of us in this field are spending most of our waking moments worrying and thinking about it and being excited about it. But I want to emphasize that no matter what we see at the LHC, the fact that we haven't seen anything already tells us that we have a solid argument for proceeding and making plans for this next generation of accelerators. And that's both in the pessimistic and the optimistic cases. The pessimistic case where we see nothing but the Higgs, then we're humbled as theorists, certainly, many of us, okay? We need to study this particle experimentally. We have a fuzzy picture from the LHC, so we have to go and look at it. Let's say we do see new particles. Euphoria, hallelujah, right? Well, let's say we see some colored particle that weighs 1.5 TeV. I can guarantee you 500 theorists will call it the superpartner of the top quark. The problem is it will not produce enough of them at the LHC to be able to verify that it even couples to the Higgs. Never mind that it does the job that it's supposed to do in more detail to solve the hierarchy problem. This is not a trivial statement, rah, 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 keep going no matter what. Had we discovered 300 GeV gluinos in the first run of the LHC, we'd be swimming in these particles by now, and then it's with millions of them, then it's not so obvious that this is the next thing you want to do. But now it is, because even if we do see them, we're going to make 1,000 of them or 10,000 of them, enough to actually produce them and claim a discovery, but not enough to be able to tell us a story about what's actually going on. And for this, you need actually a Higgs factory, which can confirm that these things couple to the Higgs, as well as ultimately going to 100 TeV to actually have that factory and study them in detail. All right, so something particle physicists love to see is pictures of the planet with big rings on them, okay? And I think one of the most exciting things that's happened in the past couple of years is that these pictures with big rings on them are being drawn. They're being drawn by our friends at CERN, who are imagining an 80-kilometer tunnel going underneath Lake Geneva. That'll be this next big step beyond the LHC. And by Yifeng and his friends in China that are drawing maps of 50-kilometer and 100-kilometer rings on the ground 300 kilometers northeast of Beijing. Okay? I think this is amazingly exciting, amazingly important, and worth putting a lot of effort into supporting both things in order to try to make sure that these machines actually go from being a dream to a reality on the necessary decades timescale. And there's the final question of the cost that always comes up. I've stolen the slide from a Yifeng. The cost of these machines is 10 billion in your favorite units. Okay, so and there's no sugarcoating it. That's how much they cost. But Yifeng has pointed out a number of times that the fractional costs of these projects compared to GDP of any country at any point in the last 30 years has always been roughly the same. Roughly 10 to the minus 4. Okay? So the SSE, when it was canceled, was 10 to the minus 4 US GDP. The running cost of the LHC now is around 3 10 to the minus 4 European GDP. The cost of these projects in China is of the same order. Okay? This is something human beings have done before. By the way, Tycho Brahe's boss, the king of Denmark, spent 8% of his GDP to give him an island, okay? And this was a really good idea because people remember this guy, except I just didn't, sorry. But people remember this guy. This is something human beings do, right? There's very few things of importance that we can do on this planet before we shuffle off this mortal coil. And this is one of them, okay? This is one of them. Am I putting you on the spot, Yuri? You know that? All right. So let me just end by saying that certainly, and not just my view, the scientific issues that we're facing today are amongst the most difficult and profound ones that fundamental physics has faced since the 1930s. It's fascinating to me that the questions that have been raised by the biggest experimental discoveries of the past 2 decades, the discovery of the accelerating universe and the Higgs discovery, they both go to the heart of something we don't understand about the combination of these ideas that were handed down to us from the first part of the 20th century. There's something we don't understand about the nature of space-time, quantum mechanics, and the vacuum. And both of these big discoveries are pointing to something that we don't understand there. In the case of the accelerating universe, our friends in astronomy have no difficulty making the intellectual case that we have to keep going, we have to measure W, we have to really know that it's a cosmological constant. All the more power to them. I support you 100%. Okay? We have a similar case that we could be making in particle physics, and we have tons of measurements we can make. There's a big, rich experimental program revolving around the Higgs avatar of these same problems. And I believe that these future circular machines are the way to go about doing them. So the scale of our vision and ambition have to be commensurate with what the science demands, and we should be more, not less aggressive in pursuing it. Thank you very much.